Okay, so I just want to remind you where we've come. We've had a look at the Schrodinger wave equation, and we've had a look at some wave functions that work with it. So when a particle is free to move along in a one dimension along an axis, we had this particular wave function, and investigating various forms of it, putting different constants in, came up with some interesting possibilities at the end, where you could have a particle where you know momentum, but you don't know where it is, you can't localize it. And from that, we got the Heisenberg uncertainty principle. So that was the first situation where we looked at the Schrodinger wave equation and we put a wave function into it. Now, the next situation we had a look at was particle in a box. And we found that when you work with a particle in a box, of course, you're confined. You can't just use the same wave function used for a free particle. You're confined to using a sine of k of x. And so because the sine has to have a certain wavelength to fit in the box, we have to have it as a multiple. The k is a multiple n pi over L. And so we ended up with quantization. We're able to put our wave function to the Schrodinger wave equation, and we got the energy. We ended up with an expression for the energy levels dependent on n as En of that. And then, of course, we went a little bit further and we had a look at the Schrodinger wave equation in the context of a potential. And we actually used a harmonic potential, but we found that the energy levels in this case are equally spaced apart, and so we've extended it, we've approximated it. We're using that harmonic in the case of a Morse potential, and from that we found that the wave number for the jump from 0 to 1 is dependent on the bond force constant and the reduced mass. So the solution of a Schrodinger wave equation in a potential gives us some very useful information about the bond. So we can go directly to spectroscopy, get our wave number for vibrational absorption, and we can calculate the force constant for a bond. Okay, so that's where we've come. And of course, you can apply the Schrodinger wave equation in various other situations as well. This next situation, again, I'm not going to go into details of solving it, but just some pertinent results that come through. I need to highlight them and let you know about them. So the next situation we're going to look at is rotational motion. And this is really important because you can imagine that this is the simplest case of one particle going around a central point, and we might think of atoms very loosely in that kind of manner. It's really important that we just deal with the moment with rotational motion. Now, there are two things that we need to know. One is that the moment of inertia can be calculated. It's dependent on the mass. It's dependent on the distance from the pivot where you push it around. And I suppose really that tells us how difficult it is to start the rotation going, or how how difficult it is to get a rotation going or to stop it. Another aspect we need to know is about the angular momentum. Angular momentum is simply the linear momentum times the distance going around. So that's gives us an idea. Of course, the angular momentum, the energy is related to these two quantities by that expression that we've got there. So we can square the angular momentum over twice the moment of inertia, and we get the energy of that particle going around. Now, these are just interesting things to note, but there's a problem with rotational motion, is that all particles have wavelength, and we know the wavelength of particles in terms of the de Broglie relation, which is h over mv. So we know what the wavelength of a particle is, and we could even fit this wavelength back into the angular momentum expression, and we would get an expression for the angular momentum as being HR over lambda. So that would be the angular momentum in terms of the de Broglie wavelength. Okay, the plus and minus here is straightforward because the particle could be going around one way, could be going around the other way. So we've got two directions. Right, so we can have a look. We've got the moment of inertia, we've got angular momentum, we've got all these quantities from physics, and we can express them in terms of the wavelength of a particle. But there's a problem with thinking of a particle as a wave going around in a circle. And the problem is here. You see, if you've got a particle that is a wave that goes round and round and round, there's going to be an issue where it meets up with itself at the end of a cycle. So you can't have it the first time it goes round, the wave being like this, and then the second time round going like this. That wave will interfere with itself in a destructive manner. The positive and negatives will cancel out, and so you will not have a stable wave at all. It will disappear. So in rotational motion, if you want the rotational motion to have any constancy to be maintained, you've got to be sure that you've got an exact number of wavelengths as that particle goes around the circle. The first time the particle goes around the circle, it has to match exactly the second time it goes around the circle. And the only way to do that is to make sure that your lambda fits in, and that your lambda is a multiple of 2 pi r over a whole number. So just like we had multiples of sine when we looked at the box, we've got to make sure that in order for the lambda to fit in, it has to fit in a circumference. And of course, that immediately leads to quantization. So your m, if your m is naught, of course you can't put it here. If your m is naught, your particle has got no rotational motion. If it's plus or minus 1, it's energy level 1, going either in a clockwise or anti-clockwise direction. Plus or minus 2, again going in a clockwise or anti-clockwise direction. And then it works out really nicely is that your angular momentum is simply h bar times this quantum number that we have now come up. And of course, then you can play around with the energy values. You can write the energy, for example, in terms of ml. But what's important on this slide, what's really important, is that we get quantization because we have to fit the wavelength into the circumference of a circle. And so this expression has to follow this lambda's 2 pi r over ml, has to work, and where your ml is your rotational quantum number. Now, I'm hoping that some of these terms are starting to become familiar when looking at rotational motion, because in atoms, certainly in the hydrogen atom, you'll recall that we'd used ml as the we'd used ml in looking at electrons. It is going to match as we come up. Okay, but of course, a particle in an atom, an electron in the atom, is not moving in a single circle around the atom. It's moving in two directions. So if we've got a particle that's constrained to go, for instance, on the motion of a sphere, you find that if you solve and you get wave functions for it, you find that the moment you're allowed to move in a spherical manner, you find that instead of just having one set of quantum numbers, you end up with two sets of quantum numbers. Okay. And those two sets of quantum numbers are the L, and the ML is dependent on the L. And of course, the ML really shows that the orientation of a rotation on the sphere is quantized. So the orientation is quantized on the sphere, and then of course you've got quantum numbers that allow for the energy. Okay, so the energy levels where L can be 0, 1, or 2, your energy levels go up like this. where when L is naught, your energy is 0. You are allowed to have 0 energy for rotation. When L is 1, then of course when L is plus 1, for instance, then you would have 1 times 2 times the moment of inertia, which we know, moment of inertia from the mass in R, and you can calculate the energy levels as well. So energy is dependent on L, but of course your orientations of that rotation are quantized on the sphere. Okay. Now it'd be nice to just have a look at some of these results and some expressions we're going to come back to are the energy expression, which is related to the angular momentum and the moment of inertia. We're going to come back to this energy expression a little bit later when we look at molecules. But just note that not all molecules are rotationally active. You see, if you want to get something that's rotating with a certain energy, and you want to give it enough energy to go to the next rotational energy level, you've got to give it an incoming photon. It's got to be able to absorb the energy from an incoming photon, which means that you need to have some differences in the atoms so that that photon can be absorbed. So you can imagine that as something rotates, if you've got a delta minus delta positive, as it rotates, it'll look like an oscillation. And that's an oscillation that viewed can be, that is the exact oscillation that a photon can interact with, and so that molecule can pick up that photon. Of course, if these are identical, then there's nothing changing here as you rotate. There's nothing for a photon to interact with, and so it's not going to be excited by a photon coming in. So you see, if you've got a molecule, for instance, a diatomic molecule that's rotating with a rotational energy level, it's going to bring in a photon with its own angular momentum to get to the next energy level. And of course, that photon has to match the difference in energy levels for rotation. So just note that some molecules are rotationally active. They're not going to absorb light. There's nothing changing with it that will interact with the light photon coming in. Okay, so I'd like to just draw your attention to certain aspects of rotational spectra. Firstly, that the reduced mass comes into play again. If you're trying to work with the moment of inertia of the one atom about the center of mass, the other atom about the center of mass, it works out that the total moment of inertia is simply the reduced mass times r squared. It simplifies things if you use the reduced mass for a diatomic system. Don't forget the energy expression I've asked you to remember, the angular momentum of the moment of inertia, and the energy levels that you have. For a diatomic system, we've got very little changes that we have to make to that. We have to just add the two angular momentum for the different atoms together over 2I, and so of course it simplifies down to a rotational quantum number. This is a different J. The rotational quantum number is also called J here, and the expression looks like this for the energy levels. Okay, so this is quite interesting because look at this expression for the energy levels. There are a whole lot of constants in it. There's h bar n, there's 4 pi ci, there's the moment of inertia, which we can calculate if we know the distance the atoms are apart. And if we know what the reduced mass is, we can calculate that. H and C are both constants. J into J plus 1, these are your energy levels. So your first energy level will be 0, so you can put 0 in. You can put 1 into that, you can put 2 into that, and you can get your energy levels from that. To simplify this expression down, though, we do have a nice little trick, is that if we can take all the constants out together with the I, so see this HC, and you've got, see this H bar of 4, sorry, this H bar of 4 pi C, that whole system together is given a name, and that's the rotational constant. Okay, so the rotational constant B is given by this expression, which means that if we put B over here in the expression for energy, we can see what the energy levels are. When J is 0, then we have 0. When J is 1, J plus 1 is 2, and you get 2 HCB. When J is 2, you get 6. When J is 3, you get 12. And so your energy levels go from 0 to 2 HCB, to 6 HCB, to 12 HCB, to 20 HCB. Those are the energy levels. Those energy levels are dependent on this B. So what I like to do is I like to have a little bit of graph paper here, and the graph paper shows more than just the energy levels. So I go up in multiples of HCB. So you start off at 0 HCB, 2, 4, 6, 8, 10, all the way up. And then you can map onto that what the energy levels for rotation look like. And the energy levels on J to J plus 1, so they get 2, 6, 12, 20. So here's 0, here's 2, here's 6, here's 12, and here's 20. And because I've got the graph paper going in between, you can see that when you absorb energy, what's the jump going to look like? So the first jump, if you've got no rotational energy and you want to jump up to the next energy level, that's the energy you're going to have. It's exactly 2 HCB. If you want to jump from this energy level to the next, you can see that difference is 4 HCB. And if you want to jump up this, that difference is 6 HCB. And if you want to jump from level 3 to 4, the distance is 8 HCB. So it's interesting what the jumps are between the levels in rotational spectra. And those jumps are dependent on the expression for energy, which is dependent on that rotational quantum number, which is J over there. So let's just show you what rotational spectra look like. If you go and you run a rotational spectra, you'll get a series of absorptions. And the series of absorptions will be at a particular wave numbers. And the difference between them will always be 2B. So you can see that if we change from an energy to a wave number, the HC will come away and you're left with a B. And so you see, what's the difference between this jump and this jump? The difference between this jump and this jump is only 2 HCB, which as a wave number is 2B. Now what's the difference between this jump and this jump? The difference between these two jumps is also 2B, 2 HCB, which is as a wave number 2B. So the distance between each of the absorptions is 2B. So notice energy jumps slowly get bigger. The energy jumps increase by HCB each time, which means in the spectrum, if you convert it to a wave number, the peaks will be 2B different from each other, which is really nice as a rule. And so if you look at the spectrum, you can say, well, hang on. The distance between the absorptions must be 2B. So let's go back a couple of slides and have a look at what B is. So if from the spectrum you can calculate what B is, just by dividing by 2, then what's the only thing you don't know in here? H bar is a constant, pi is a constant, C is a constant, I is the moment of inertia. You can calculate the inertia simply by looking at the rotational spectrum and knowing that the distance between the bands is 2B. So you can calculate the moment of inertia directly by looking at the spectrum. Okay. So there, I will detail exactly how we use the energy expression in a couple of slides' time. But meanwhile, first thing I want to do is I want to take my graph paper away from this and actually show you what the energy levels look like for carbon monoxide and hydrogen bromide. So here we go. This is what carbon monoxide looks like. I know what the distance is, but the bond distances are for both of them. I know what the reduced mass is for both of them. I've calculated it. And so I know what the moment of inertia is for both of them. So if I know what the moment of inertia is, I could work my way back and determine what B is, and therefore what the distance between those spectra is apart. Just a little point on this is I'm interested in how these energy levels are populated. Okay, so just note that we do have the Boltzmann constant, and it'd be interesting to see how these levels are populated. Just be careful, because these are the energy levels, but remember for rotation in one dimension, the first rotation, that it could be moving forward or backward. And of course, if it's moving forward with a certain angular momentum or backward with a certain angular momentum, the energy is the same, which means that there are multiple energy levels available. So if there are multiple energy levels at level number 4, for instance, then calculating the populations is not going to be simple as comparing one against one. We need to know how many are in this, how many are present there to compare it. So we might have to adjust the Boltzmann distribution to account for there being several levels at energy level number 6. But just to give you an idea with carbon monoxide and hydrogen bromide, that I would like to get a delta E into this Boltzmann expression. That's easy to work with. And a delta E that I'm going to work with is this value here. That's up to here. Here's naught. And the delta E I'm going to work with here, which is KT, which is 4 times 10 to the minus 21 joules. 4 times 10 to the minus 21 joules is slightly more than the distance from level 0 to 4 for HBr, and slightly more than the distance from level 0 to level 9 for CO. But that KT, I want to work with it because it's nice and easy to put into Boltzmann distribution. If you put exactly KT at 25 degrees into that, the KTs cancel out and you get e to the minus 1, and then the difference in populations is about 36%. So at energy level 0, up here you would have about, if you've got 100 particles here, at here you would expect about 36 particles. So if there are 100 here, you would have about 36 particles over here. So you can see that at normal temperatures, all of these levels are going to be quite well populated. So you'll have energy level 0, 1, 2, all the way up to 9, having particles with those energy in. And so it's interesting that the spectra that you get has a range of intensities that are related to the populations of these energy levels. Okay. So don't forget Boltzmann. We won't go into it, that the presence of other levels means that you might need to modify Boltzmann. But I'm going to use Boltzmann as is to say that, well, hang on, if you've got 100 particles here, at this point here, at level 9, you've probably got about 36 particles here. Level 5, you've probably got about 36 particles, which means that all of these levels are really, really well populated to varying degrees. Of course, more populated towards the bottom and less to the top, and that's why you get this range of intensities when you run the spectra, when you get rotational spectra. Okay, but I've got another use for rotational spectra. Imagine, okay, how do we get the value of 36 again? Right, so just imagine if we want to work out if I can just run through this again, if we want to work out the relative populations, say we've got 1,000 molecules, are they sitting at energy level 0? Are they sitting at energy level 11, for instance? Where are they sitting? We've got the Boltzmann distribution that tells us that if you want to compare two energy levels, what you need to do, if you've got two energy levels, you need to know what the difference is, and you can work out the relative populations using the Boltzmann distribution. So what I've chosen as a reference, because I don't want to do it for every level, is I've tried to choose a delta E that fits, everything will cancel out really quickly. So I'm going to choose a delta E of exactly KT, which is this exact number. So if I put KT in here, you end up with 0.36, you'll end up with 36% or 37%, which means that if you've got 100 molecules at energy level number 0, there will be 37 at this energy level. If you've got 100 molecules at energy level number 0, there'll be 37 over there. Okay, so that's how I'm getting the value of 30, 36, 37, is that using the distribution at 25 degrees, and if you've got 100 there in your sample, 36 or 37 will be sitting up at KT. So if you had a sample of HBr, of course, at 25 degrees, they will all have different, if you looked at each individual molecule, they would have different rotational energies, and you could look and try and see what the distribution is, and you would know that for every 100 molecules you found at energy level number 0, you would have about 36 or 37 at energy level number 5, which is quite close to KT. Okay, does that explain how we found the value of 36 again?
Yes, it does.
Okay.
Thank you.
So the distribution gets that. And then I'm going to go back to the other questions, the difference of 2B. So what's important, this is the real important result from rotation of two masses. Of course, we've got quantization. We've got to make sure that as you go around, the wave is not destructive. And so what happens is that your energy levels are given by this energy expression. Straight from the Schrodinger wave equation, if you get a wave function out, your result is that your energy levels are going to be like this, where B is this rotational constant over here. So it's quite a complicated solution to the Schrodinger wave equation, but it's incredibly useful to us because the solution says that you have to have these rotational, your rotation is quantized, and that J values have 0, 1, 2, they have to be whole numbers. So you can't just have any energy level. And so if we put 0 into this, we'll get the lowest energy level. So 0 into here, J is 0 times 0 plus 1. That whole thing is going to drop to 0. Energy level 1, we put 1 into here. And so it's HC into 1 times 2. And you'll get the next energy level is 1 times 2 is 2 times HCV. For the next energy level, if you put 2 in there, you'll get 2 times 3 is 6, and so you'll get 6 HCV and so on. And 3 times 4 is 12, 4 times 5 is 20. And so these are your energy levels. Okay. Now, of course, it can only, you can only go up one energy level at a time. It's going to absorb a single photon to go from one energy level to another to conserve angular momentum of the photon coming in. And so your absorptions will be from level 0 to 1. Your next absorption will be from 1 to 2, from 2 to 3, 3 to 4, for instance. And of course, at 25 degrees, we know the population, so it can occur. So we'll definitely have some molecules at energy level number 3 that will be able to absorb. We'll have molecules at energy level number 2 that can absorb, etc. But what's interesting is what's the difference between these energies? So this energy of absorption, What's the difference between it and the next? Well, the difference between it and the next, let's have a look at the difference between this jump and that jump. Can you see that that difference between those two jumps is 2hCV? And what about the difference between this jump and that jump? It's also 2hCV. The difference between this jump and that jump is also 2hCV, which means that if you convert it to wave numbers, if you convert it to a wave number from an energy, remember wave number is 1 over lambda. If you convert it to a wave number, that difference is not 2hCV, but it's just simply 2V. So the difference between these two is 2V, these is 2V, these is 2V, and that is 2V. In the spectrum, the peaks will be 2V different from each other in a rotational spectrum. Okay. So does that answer the question why the same difference of 2V?
Yes, Prof.
Okay.
Thank you.
Right. So how do we use this? Right. So this is straightforward. If you've got a molecule, you know what it is. If it's HBr, you know what you know what atoms you've got. If it's CO, you know your atoms. And if you know your atoms, you know their masses. And so you can easily calculate the reduced mass of that molecule. Okay. So the first thing you do, like we did in vibrational spectrum, the first thing you do in a diatomic system is you calculate the reduced mass of the system. Okay.
Okay,
just hang on. Just hang on. So please unmute yourself if you've got a question. Okay. So first thing you do is you calculate the reduced mass. The second thing is you can go to experiment and you have a look at the spectra. And because we know that the difference between the peaks in a rotational spectrum and a microwave spectrum, if the difference between the peaks is 2b, then what we do is we take and we divide it by 2 to get what b is. Now we just need to know how to relate b to the moment of inertia. And the way we relate b to the moment of inertia is through all these constants. And so if you've got b, which we can get from the rotational spectra, we can calculate the moment of inertia. But of course, we know the moment of inertia for a diatomic system to be mu r squared. So if we know what the moment of inertia is from the rotational spectrum, and we know the reduced mass, can you see what we can find in here? We can calculate the bond length. Okay, so this is a workflow that we can work through to find the bond length. And how did we get here? Well, because from the energy levels, we have this constant B. The energy levels from rotation, we have this constant B that's come out. And that constant, that rotational constant is dependent on the rotation moment of inertia. And we can then, if we know the moment of inertia, we can get the bond length. So this is a really powerful slide showing the results, because remember last lecture we calculated K, but of course in molecular mechanics K is not the only thing you need. You also need the equilibrium bond length. Okay, there's a question here. How can we find the mass of one atom using grams per mole to just gram for one atom? Okay, that's a really good question. First thing I would do is I would work in kilograms. So I'm answering your question, but in a slightly diverse way. So first thing you need to do is, if you know you've got 1 gram per mole for hydrogen, please change it to kilograms and say as well as 0.001 kilograms per mole for hydrogen. Now, how about for one atom? We just need to divide them by Avogadro's constant to get the mass in kilograms for one atom. Does that help? Also,
yes, that's fine, thank you.
Also, I have a constant that works out really nicely. So please have a look on Are You Connected on the table of constants. I've got a simple factor that you multiply by to take you straight from your atomic mass units directly to kilograms per atom. So have a look at that. That might save a lot of work on that. Okay. So today, there are two things that I really want you to take home from this, is that when you have a diatomic system that can rotate, it is not allowed to have any rotation. Those rotational energy levels are quantized. And the energy levels are given by Ej into Hc, J into J plus 1b, where J goes from 0, 1, 2, 3. That's your energy levels. And of course, B is tidying up a whole lot of constants together with the moment of inertia. That's the first thing. So your rotational energy levels are given by this expression here. And second thing that's really important is that we can take from that, if we've got a spectrum, we can work our way to B, and we can work our way from B to exactly the bond distance that we would require in terms of molecular mechanics. Okay. Right. A little later this week, I'm going to, so tomorrow or the day after, I'm going to put on some problems on Are You Connected related to previous work we've done, particularly with regard to the vibrational spectra and also with rotational spectra. So look out for those. I'll alert you when they are there, but also have a look at the TUT. At the tutorial, there are some examples where you're given spectra. And of course, you know what the atom is, so you can calculate mu. See, can you work from the spectra to calculate the bonding? Or, on the other way around, if I gave you a molecule, a diatomic molecule, with a particular bonding, would you work your way back to be able to predict what the distance is going to be in terms of the spectra? Okay. Are there any questions? Okay. So please, as always, if you do have questions, get hold of, you can email me and I'll answer as best I can. Or if it's something you want me to run through in class, let me know as well. And we'll carry on with this at 11 o'clock tomorrow. No questions? Okay. So I'll see you all then at 11 o'clock.